This is the third question from the 2018 Physics C Electricity and Magnetism exam. If you look in the notes, the link to this question and the solutions to this question is there, straight from the College Board's website, with a lot more useful information that you have. So please explore that link. This is just me working through those solutions. My suggestion to you is to get the question, work through the question first on your own. Try to do it in the time of 15 minutes. That's about normal for an AP question. It's not going to feel like enough time. And then kind of watch me work through the question. It's gonna help your thinking through it a little bit better. So let's jump in. We have two figures here. One is wire 2, current running to the left. I2, wire 1 running into the page with current, running out of the page with current I1 there. So that's the sort of side view of what's going on. And then the top view, you can see that you have wire 2 current running to the left, wire 1 current running down, but they are not sitting on top of each other. They're separated by a distance of d. So that's what those two diagrams give you. Question A is use Ampe's law to derive an expression for the magnitude of the magnetic field at point P due to wire 1. So when we use Ampe's law, what we need to do is draw an Amperian loop around wire 1. And then our path of integration is going to kind of start at point P and move in this direction, because that's the direction of the magnetic field from wire 1 using your right-hand rule. This is just for the magnetic field there, just the magnitude. So we don't need the direction yet, but we will eventually. And so since it's Ampe's law, we should write down Ampe's law. The integral of B dot dl is equal to mu 0 times I enclosed. Now, since the magnetic field around wire 1 is going to be parallel to this Amperian loop the entire time, the magnetic field comes out, and it's just going to be the magnetic field times 2 pi d, that's the radius of that Amperian loop we used, is equal to mu 0 times I1. That's the amount of current there. So the magnetic field from wire 1, so we'll call that B1, is mu 0 I1 over 2 pi d. In order to get full credit for this, you really have to show that you're using Ampe's law to find that. Then derive an expression for the magnitude of the net magnetic field at point P. So if we look at point P, we know that we're going to have a magnetic field from wire 1. I'm going to go ahead and just draw that in. That's B1 that we just found. And from wire 2, we're also going to have a magnetic field. So if you take your hand, make a thumbs up, stick your thumb in the direction, this is your right hand, of current 2, you'll see that magnetic field 2 is going to go into the page at that location. So if you wanted to look at point P, magnetic field 1 would be coming out of the page, and magnetic field 2 would be going in this direction. So if I want the total magnetic field there, it's the vector sum of those two. They're 90 degrees to each other. We found B1. B2 is going to be similar to that. We'll go ahead and write it right there. B2 is mu 0 I2 over 2 pi, and we're the same distance d away. So if we want the total magnetic field at point P, it's going to be the vector sum of those two things. The total magnetic field is going to be the square root of B1 squared plus B2 squared. Because they're 90 degrees to each other, if we had another view, we'd have B1 in this direction and B2 at 90 degrees to it. So it'd be kind of pointing in that direction. I want the hypotenuse of that. So my total magnetic field, to give us a little bit more room, is going to be the square root of mu 0 I1 over 2 pi d squared plus mu 0 I2 over 2 pi d whole quantity squared. Now, they tell us that I2 is equal to twice I1. So let me just kind of zoom in on this. My total magnetic field is going to be the square root of mu 0 I1 over 2 pi d squared plus mu 0 times 2 I1 over 2 pi d squared. So what we can do here with our fun little square root thing, we can pull out mu 0 I1 over 2 pi d quantity squared, and that's going to be times 1 squared plus 2 squared. So that total magnetic field is going to come out to be mu 0 I1 over 2 pi d times the square root of 5. That would be my total magnetic field at that point. It's those two things put together. It's really hard to see how those vectors go together, but knowing that they are at 90 degrees to each other helps us find their vector sum in this way. Part C, calculate the numerical value of the angle to the horizontal for the direction of the net magnetic field at point P. So, cool. All right, so what we want is the angle to the horizontal. If we look at this diagram here, B2 is into the page and B1 is up. So what we want is the angle of the net magnetic field to the direction that B2 points. That's the horizontal direction. And so if we sort of adjust the way that we're looking at that, B2 points in this direction and B1 points this way. And so what we want is that angle. So here, this is for part C. So the tangent of that angle is equal to opposite magnetic field 1 over magnetic field 2. So the tangent of that angle is mu 0 I1 over 2 pi d divided by mu 0 times 2 I1 over 2 pi d. So the mu 0's cross out, the 2 pi d's cross out, and the i's cross out. And the tangent of that angle is equal to 1/2. So that angle is equal to the arctan of 1/2. And that angle comes out to be 26.6 degrees. What's really interesting here is that they are asking you for the numerical value of the angle. So you have to find that actual angle value. You can't just sort of leave it in terms of that. So you know at that point that everything is going to have to cross out except for numbers. So for this last part of the question, we're going to take wire 1 and let go of it, and we want to see how it moves, and we're not going to worry about gravity. So let's go and look at what's happening with wire 1 in the field of wire 2. So if you look at wire 1, magnetic field 2 we said was into the page for the location of wire 1. So if we look up here, that means where wire 1 is, the magnetic field points in this direction. Right above wire 2, the magnetic field is back, but here the magnetic field is into the page, and on this side the magnetic field is out of the page. Now, each one of those is going to cause a force to be on the wire. So if we look at the top of the page, using our right-hand rule where we make sort of a little finger gun here, with the current running down and the magnetic field into the page, I'm going to get a force in this direction here. The magnetic field's coming out of the page. At the bottom, the force is going to be that way. Now those forces are equal in magnitude. So with those forces being equal in magnitude, we're not going to see any movement. But what we do see, so there's no movement. It's not going to slide to the left or to the right, but we are going to see a torque. And that thing is going to rotate clockwise as viewed in figure 2. And then your justification for that answer needs to be an explanation of figure 2. So that's what's going on part D. So if we move down to part E, I'm going to talk about flux a little. We want to find the flux through this rectangular loop now. We had wire 1 there, we've taken it out, we've got this rectangular loop, and we want to see the correct integration that's going to give me the flux through this rectangular loop. So looking at wire 2, the magnetic field that it creates above it is going to be into the page. And it's telling me now that the current looks like this. So my magnetic field at this location from Ampe's law, we said, was mu0 I2 over 2 pi d. I don't want that to be d anymore because we're not staying at the location d. It's going to be over 2 pi r. So my magnetic field at this location with the current that they give me is mu0, sorry about that, I2, I'm sorry, it's mu0 times 2I0 times 1 minus kt over 2 pi r, because it's going to change, because that magnetic field is going to decrease in magnitude as we move in that direction. So if I want the flux, I have to take this and slice it into tiny little pieces of differential area that are length L long and dr wide. So if I want to get my flux, that flux is going to be the integral of b dot dA, and that integral is going from d to d plus w. That's going to get me this length right here. I'd have to start at this location, and it's going to be the magnetic field that we found times the differential area that we're talking about. So from d to d plus w of the magnetic field, mu0 times 2I0 1 minus kt, need a little bit more space, over 2 pi r times the differential piece of area, so it's going to be the length that doesn't change, times dr. That's going to be the setup for what's going on right there. And since they're just asking us for the setup, we got to find the one that looks like that. So the one that has the correct limits, first off, eliminates these two. And then it's not LWdr, it's going to be LdR. And then they go ahead and take that integral for us, which is really, really, really nice. And they tell us that the value for flux is given here. They want an expression for the magnitude of the current induced in the loop. So what we have to do is take the time derivative of the flux. So the EMF is change in flux over change in time. And then we're going to divide that by the resistance that's given. So looking here, the only thing that changes in time is this piece. So my EMF is going to be mu0 I0 L, and then that thing, when we take the derivative, just gives me negative k times the natural log of d plus w over d. That's going to be my EMF. There's a negative sign there, so those negative signs go away. So my current is going to be that value for EMF divided by R. So mu0 I L k times the natural log of d plus w over d over the resistance. So we have to take the derivative. The only thing that's going to have the derivative of it is that piece. So, no, I left out the pi. I apologize. There's the pi. Just going to take an easy time derivative of this, which is quite simple. What's the direction of current, if any, induced in the loop as seen in figure 3? So for this, what I really like to do is say, okay, what's the direction of the magnetic field? What's the direction of the change in flux? What's the direction of the induced magnetic field? And what's the direction of the current? So looking at it, we know that our magnetic field is going to be into the page right there. And looking at our function for current, looking at our function for the magnetic field that we had above, since that initial current is decreasing, my flux has this negative kT thing with it. My magnetic field is decreasing as time goes on, so my magnetic flux is in the opposite direction, which means the induced current is into the page, which means the current has to be clockwise. All right, that's our third question. Thank you for watching, and I hope this helps.